Today we'll learn about some methods for combining machine learning models to get a single model which performs better than any one of the original ones. And there are a couple of different approaches to doing this, one called bagging, which consists of subsampling the data with replacement and training the model on those subsamples. This way we get several model results and they'll be somewhat decorrelated because they're trained on different data. Then we can combine the outputs of those models by averaging for a regression problem or by taking plurality vote for a classification problem. A little more sophisticated method is called boosting. The general idea of boosting is to train a model, then take note of the deficiencies of that model, and train another model that's meant to address that. So you can weight the observations that the first model did poorly on. That's called AdaBoost. Or you can take a difference between the observed response values and the output of the first model and try to fit that difference. That's called gradient boosting. So let's explore each of these approaches. In problem 1, we're asked to give an example of a technique in math where we approximate a function by adding a sequence of functions, each of which is designed to make the running sum as close as possible to a target. And there might be various answers here, but what I had in mind was Taylor series. So just as a reminder, the way Taylor series work is you have a function like this exponential function, and you want to represent it using a simpler function like a polynomial. So you start with the constant function that best approximates the target function at a given point, in this case the origin. Then you add that to the multiple of x that best approximates the function. In this case, that's just going to be the function that maps x to x. This is shown in orange here. So if you add the original constant function plus this orange function, you get this green one, and that's approximating the exponential as well as possible, given the constraint that you're only using a linear polynomial. Then we use a quadratic term, and now we're fitting the blue curve even better, and so on. As we add higher and higher order terms, we get a better and better approximation of the exponential function over an interval centered at 0. So this is sort of a pure math analog of what we're going to see when we do boosting, where we have a target we're aiming for given by the response values observed in the training set, and we're reaching for it additively, but we're restricting ourselves at each step in some way. In the Taylor series case, we're restricting to polynomials of a fixed degree. In the case of gradient boosting, each step is going to be given by a machine learning model. So in problem 2, we start thinking about bagging, and the point here is to ask, why does it help to have decorrelated predictions? Why, when you average predictions that are not perfectly correlated with one another, do you get a predictor which is better? And the reason is going to be that the variance goes down. And we can see that with a formal calculation. So we're asked to show if we have identically distributed random variables, which are not independent, they have correlation rho, which is positive, but they all have the same variance. That when n is large, so this term is small, the variance ends up going down by a factor of rho relative to any one of the y's originally. So let's show that this formula holds. In problem 3, we're going to implement bagging for a particular simple regression problem where our feature space is one-dimensional, represented here by x, and our response variable is continuous. So we want to fit a bunch of decision trees to these data and specifically fit them on with replacement samples of the original data. So let's say we do 100 models. We'll start by creating an array of models. Each has max depth 2. And these are decision tree regressors coming from the decision tree package. So what we need to do is train each of these models. And because the x data here are stored in a separate array from the y data, which is the standard thing to do, what we need to do is come up with the indices for our sample and then use that index object to extract our sample from both x and y at the same time. So we'll call it ins for indices, and we'll sample from 1 to the number of rows of x. And let's say we take 50 observations. And then we want to fit the ith model using x subsampled on those indices, and similarly for y. And what we find if we run this cell repeatedly is that we don't get a lot of variation. So it's actually the case here that the predictions made by these trees are decorrelated enough that when we average the result over many of them, we end up with low variance. So that's consistent with this calculation we did here, where we start with some original variance sigma squared and then it goes down to rho sigma squared, where rho is the pairwise correlation between predictions y. So AdaBoosting, unlike bagging, is not readily parallelizable. We're going to fit a model and then we're going to fit the second model based on how that first one did, and then a third one and a fourth one and so on. And the idea is going to be to fit the first model to the data as normal and then look at the points that weren't fit very well. So the shading comes from this marker Z keyword argument, and it's saying let's make a prediction and then compare that to the actual response value and square it. So this is a squared deviation error. And so you can see these dark blue ones are far from the prediction, likewise here, whereas the ones that are closer are colored white. The color gradient scheme we're using is from white to blue. So then the second model needs to look at the same data. So unlike bagging, it's not subsampling the data, but it is going to put extra emphasis on these points that are far away. And then what we'll do in the end is recombine all these models based on how accurate they were for various points. But when we go to train the second model here, we need a way to say these points are high priority and these other points are lower priority. In other words, we need to be able to weight our training observations. And that's not something we've talked about how to do, so we have to think about that. And it's a useful exercise. How can we alter the decision tree training process to give points priority in proportion to some given weight instead of giving every point equal priority? So the way decision tree regression works is that we consider a split, let's say, at this particular x value. And then we look at the function which is piecewise constant with a break right there, which has minimum mean squared error. So it's going to resolve to the mean of the points to the left on the left side and the mean of the points to the right on the right side. And when I say mean, I'm talking about the mean of the response values. And then we consider just adjusting this threshold and asking, where do we get a minimum mean squared error? And the key point is the mean in this mean squared error is implicitly referring to a uniform distribution. When we add up a bunch of numbers and divide by how many there are, we're saying that each point needs to be weighted equally. So what we can do instead if we have a weight function is just replace that uniform weight with our new weight. Likewise, when we look at classification trees, when we compute the Gini impurity, we count the number of reds and count the number of blues and use those values for the calculation. But counting is really the same as adding with weights of 1 for each observation. So we can replace each of those counts with a sum of weights. Rather than just counting the number of points, we can add up the weights that go to that side. So we aren't going to implement AdaBoost here or go further into the implementation details. But I did want to take this opportunity to draw attention to the idea of weighting training observations, and especially how to generalize ideas that treat all points equal by replacing counts with sums of weights and by replacing ordinary averages with weighted averages. So finally, we'll look at gradient boosting for this same parabolic shaped data set. So the idea is that we'll start with 3 models, and then we'll train the first model on the original data. Then we'll train the second model on the difference between the original y values and the y values predicted by the first model. And then we'll train the third model on the difference between the desired y values and the sum of the first 2 models. So the models will combine by addition to approximate y. So we'll make a plot here showing the original data in blue and then the first model fit in purple. And then blue minus purple gives you these green points. And then the second model fit is shown in purple in the second plot. And then the purple subtracts from the green to produce the peach points. Finally, this decision tree matches the peach points as well as it can. Then we add together these 3 purple curves to get this tomato colored curve to fit the data. So part C asks us to compare boosting decision trees to simply increasing the depth of the tree. If I just show you this final tomato curve, you might think, well, it just looks like a decision tree with a fairly high depth, enough to get several breaks here. But from a training point of view, it's quite different, because whenever you make a split in a single deep decision tree, you've fragmented your data, and you're bound to that split for the rest of the training process. Whereas in this boosting scenario, we're not fragmenting the data. At each stage, we're able to consider all of the data again. It's just that the data are shifted down vertically. And also, we don't really have to think about the split anymore. It does shift the data, but otherwise, we can put the splits in totally different places for each model. So in summary, bagging entails training on with replacement samples from the original data, and then taking an average for a regression problem or a plurality vote for a classification problem. AdaBoost entails weighting training observations based on the fits of previous models. Lastly, gradient boosting entails training models on residuals of sums of previous models.